I'd like to thank you guys all for being here today. We're super excited to share what we built with you. My name is Dan Gertismeyer. I'm the software development manager for AWS Fargate. And to my left here, I have Archana Shrikanta, senior software engineer for AWS Fargate. We have a lot to cover in our presentation today, so we're just going to go ahead and dive right in. The goal of this talk is really to provide you with information that you need to know to be able to get started with Fargate right away. In order for us to cover all the details that we want to cover and to make them tangible, we have structured this talk as a progression. In this progression, we're going to step through building a tic-tac-toe web app called SCOREKEEP that takes advantage of many of the ECS and Fargate features. The application is made up of two containers, a front-end container that uses Angular and Nginx for all the page elements, as well as a back-end Java Spring container that uses RESTful API requests that are forwarded on from Nginx. The front-end container is responsible for user interface, and the API container is responsible for all the business logic, as well as integrating in with DynamoDB for stateful storage and SNS to notify of game completion. If you'd like to run through the setup yourself, this package will be available shortly after this talk on GitHub under our AWS Labs project. We've broken down this talk into 5 steps, and each of these steps will provide an overview of how it works with Fargate, walk through the configuration options that are available regardless of if we use it in this application, as well as select the configuration option that sort of best fits our use case. At the very end, we'll demonstrate the application running on Fargate, we'll pull it up in the AWS CLI, show you the repository, and then go into the ECS console to launch the task and the service. But before we get started with that, let's go ahead and do a quick overview of the constructs in Fargate. As Fargate is exposed through Amazon ECS, the constructs are going to be identical to those that are used to today in Amazon ECS. We built it in a way to enable the migration between bringing your own EC2 instances and utilizing Fargate based on the level of control that you need. So the first construct is the task definition. The task definition is like a blueprint or a recipe for your task. It's where you configure all of the relevant parameters for the container set that you want to run. Now, after the task definition, we have the cluster construct. And now you may notice that we are still defining a cluster despite not needing a cluster of instances. However, this construct is still very useful as it serves both as a logical abstraction to organize your task together into collections, as well as a boundary for permissions and isolation. You can set up IAM policies on your cluster to prevent users from being able to run tasks in a particular cluster, and you can permission it down to a limited scope of resources. And ECS clusters have the ability to run both tasks in Fargate and tasks launching on EC2 instances that you bring simultaneously. And so this offers you flexibility to organize your resources regardless of if you want to run it on Fargate or on top of an EC2 instance that you're bringing. Next, we have the task, which is simply an instantiation of your task definition. Once you launch, you may override parameters in the task definition, as well as specify runtime-specific parameters. And it is here that you're going to specify Fargate as your launch type in order to take use of Fargate. And now tasks are great. However, oftentimes you need multiple copies of a task, and you don't want to worry about a particular task failing. So that's why we have a construct of services. Services are very similar to the EC2 autoscaling concept and allows ECS to keep multiple copies of your Fargate task running. You can use your services with an optional load balancer to load balance between the tasks. For Fargate, we support both the ALB and the NLB load balancer. And services are also valuable for updating copies of your tasks with a single API call. Now that we've reviewed those constructs, let's jump back into configuring our SCOREKEEP application. You remember that a task definition is like a blueprint or a recipe for your task. By specifying information about your containers up front, it makes it easy for this configuration to be shared and have reproducible task launches. To the left, you will see that we have a start of our task definition for the SCOREKEEP application. The first thing we define is the family. As a task definition runs our immutable version documents, the family provides a friendly way to reference a set of versions. Next, we have the container definitions block, which defines the containers that we want to run as part of this task. Note that containers defined in tasks will be started at the same time and will be co-located on the same host. For our SCOREKEEP application, we have configured our front-end container talking to our API container on localhost, and so we've put them in the same task definition so they can communicate over that localhost interface. However, if you were building an application and you wanted to have the containers be able to scale or deploy independently, you could also split these two containers out into task definitions and talk to them through a load balancer or through an IP address. When using when using AWS Fargate, you can specify the images from an Amazon Elastic Container Registry, which uses IAM permissions to perform the image pull operation, or you can use it with any public repository. And so this snippet here represents the core of any task definition. It's all required information that you need to get started, and you're going to find it no matter what container management solution that you use. So let's first add in compute to this. For those familiar with ECS, the units have been kept the same. You can specify CPU and CPU units, and you can specify memory in megabytes. However, we have introduced a new concept known as task-level resources. And these task-level resources that allows you to set a ceiling for the total amount of resources that your task can consume. And so this gives Fargate information it needs to be able to allocate the correct capacity on your behalf when launching your task. Task-level resources are the only required resource parameters with AWS Fargate. And now you may notice here that on the left-hand side of the screen, I have units in CPU units in megabytes, but in the right half, I'm specifying it in vCPU in gigabyte. With task-level resources, we support the ability to specify alternate units so you can write them in a way that feels natural to you. For those of you familiar with ECS, container-level resources are still available with AWS Fargate, but these resources are now made optional when using task-level resources. And so to get an idea about how all this works together in practice, let's go through it step by step. And so let's first start with CPU. As previously mentioned, the CPU is the total amount of CPU allocated to your task. By default, each container is given an equal share of the available CPU when under contention. If there is no contention, the containers can then burst up to the total amount of CPU specified at the task level. Occasionally, sharing is not a desirable behavior, or equal sharing is not a desirable behavior. Sometimes when you have a task that behaves poorly when it's not given enough CPU, and you want to be able to allocate additional units to it. Other times you have a sidecar task that is performing offline processing, and you don't want to be able to give it as many units, and you want to specify a smaller amount. In both these cases, you can configure a ratio of the CPU units given to each task up to the amount given in the task level CPU. While this is not necessary for our SCOREKEEP application, we've decided to configure our CPU for the purpose of illustration this way. We've allocated 3/4 of the shares to our more resource-hungry API container, while we've allocated 1/4 of the shares to our Nginx front-end container. And we do this by specifying the values of 256 and 758 in the respective container definitions. So moving on to task memory. So task memory is the total amount of memory allocated to your container when you use your task. If you just specify task memory, your memory will be allocated based on the behavior of the Linux memory allocator up to the task maximum. And so it's a little bit of a first come, first serve model. To customize this behavior further, we have 2 container level parameters that you can specify. One is called memory, and one is called memory reservation. And these can be used in conjunction with task memory. The first one we'll go over is memory reservation. So memory reservation is a soft lower bound for the container to operate in. The lower bound is used as metadata to the memory allocator, and that metadata is used to signal the kernel to reclaim memory down to that level when memory is under contention. And so in this example here, if the SCOREKEEP API container were using up a large amount of memory and memory were to be full at the task level, the kernel would prompt the memory allocator to look at opportunities to bring the SCOREKEEP API container back down to a respectable level. The other container option that we have is memory. And memory, when specified at the container level, is similar to memory when specified at the task level. It serves as a hard upper bound where the container will be killed if it tries to go beyond this value. The typical use case you have here is that you have a non-essential container that when packaged with your task, you would like for it to be killed rather than bringing down the entire task. And so let's say that you had a log driver where the logs were not business critical, and so you'd like the logs to be sent out, but if for some reason this log container were to be taking up too much memory, you would rather have the task continue running without it than for the entire task to be crashing. So putting this all together, this slide shows all the available task level resource configurations available for Fargate. There's over 50 configurations here to allow you to efficiently allocate the resources to your Fargate tasks, ranging all the way from 1 virtual CPU and 512 megabytes of memory, all the way up to 4 virtual CPUs and 30 gigabytes of memory to find a task size that fits for your use case. And when you pick these sizes here, you pay just for the resources that you're provisioning at this task level on a per second basis with a 1-minute minimum. Now, before I hand it over to Archana to talk about networking, I'd like to take the time to talk about platform versions, as it has some relation to the CPU memory concepts that we just went through. So platform version is a new concept into the ECS API with AWS Fargate. And your platform version refers to the runtime environment outside your tasks. This includes things like the container runtime and the Linux kernel. Now, you may be thinking, great, but why do I care about this? Isn't everything just packaged inside my container? And while it is true that all your dependent libraries may be packaged inside your task, your application interfaces directly with the Linux kernel to make system calls and utilizes underlying file systems provided by the platform and the host. And so as we make improvements to Fargate, some of these will change, and we want to provide the transparency into the details, as well as enable control to be able to test and validate before you adopt any new platform version in case there's any adverse side effects. To specify a platform version at launch, you can either specify it with -- platform version and the version at the end. You can specify it with the tag of latest, which will always pull the latest platform version, or you can leave it blank, which will just give you the latest platform version. Platform versions are backwards compatible for the vast majority of workloads, so we do recommend adopting the latest version to always stay up to date with the latest features and fixes, and to only go back to previous platform versions if you experience any sort of issue. So with that, I would like to turn it over to Archana Shrikanta, who will talk to you a little bit about the remaining configuration options and features of Fargate.
All right, hi everybody. Thank you, Dan. So I'm going to talk to you now about networking and some of the other features that we've built for Fargate. So from Dan, you heard about how you can configure CPU and memory resources for your Fargate task. But in most cases, just giving your application compute resources is not enough. You need some kind of network connectivity to your task. So in this section, we're going to step through one step at a time exactly how you can configure the network around your Fargate task. So all things networking within AWS always starts with the VPC. And many of you are probably already familiar with VPCs. It's very widely used across many AWS services that also need networking, like EC2, ELB, RDS, etc. But for those of you that are not aware what a VPC is, VPC stands for Virtual Private Cloud. And it's AWS's way of giving you your own private network on the AWS cloud. And what this means is that your VPC is associated with a set of private IP addresses that are not exposed on the internet that get allocated to the various AWS entities that you may launch into this VPC. So in our example here, we have a VPC that's associated with an address range of 172.31.0.0/16, which is the CIDR notation for all IP addresses that start with 172.31. The next thing you would do is create a subnet inside of this VPC. Subnet, as the name suggests, is a sub-network within your VPC, and it gives you a way to carve out your VPC into smaller networks. So in this case, our subnet is associated with an IP address range of 172.31.1.0, which is a subset of the IP address ranges of your VPC. So now you have a network set up on AWS, and you're ready to launch some Fargate tasks in here. So when you launch a Fargate task using the run task API, you're going to launch it into one of these subnets that you just created, much like you would launch EC2 instances into subnets. And what happens underneath the hood is that we create an elastic network interface in the subnet that you pick. This elastic network interface gets a private IP address from the address range associated with your subnet, and then we attach that ENI to your task. So now your task has a private IP address from your VPC. And all the containers within this task can use that IP address to interface with other private entities in your VPC without having to go over the internet. But you can also choose to assign public IP addresses to your tasks if you want your task to be addressable on the internet. And we'll go through the details of exactly how you can configure these things. You can also use security group rules and define fine-grained inbound and outbound rules to control exactly what kind of traffic is allowed to and from your tasks. Again, that's a VPC feature that's been available with EC2. It's now available with your Fargate tasks. And one last thing about subnets before we move on is when you create a subnet, it lives in a specific availability zone. And as many of you may be aware, each of AWS's geographic regions are divided into availability zones, and these availability zones are designed from the ground up to have independent fault characteristics from one another. So we highly recommend that you create a subnet in multiple availability zones and spread your tasks across these subnets so you can build that redundancy into your application. All right, so what does the API experience look like around networking? So this is the task definition that Dan already has gone through, and we're going to start to layer in some networking parameters in here. The first thing that you need to set is a network mode parameter in the task definition, and you will set it to AWS VPC. And that's what tells us that all the tasks that you will run against this task definition, you intend to run it inside of your own VPC. And then on the run task API call itself, you give us a pointer to your task definition, which is similar to the ECS experience. And then there's a network configuration parameter on here. And in this parameter, you give us the subnets and the security groups that you want to associate with the Fargate task that you're going to launch. And as you can see here, you can provide us with a list of subnets. And if you do provide us with more than one, we will automatically pick a subnet from that list to launch your task into in a manner that optimizes that availability zone spread that I talked about across all the tasks that are running against that specific task definition family. All right, so now we know how to launch a task. We know how to have your task be associated with a private IP address from your VPC. And all the network traffic to and from your application that's running within the Fargate task is going to go over this task ENI that got attached to it. And oftentimes, a common access pattern with many applications is that it requires either inbound or outbound or both access, inbound or outbound access to the internet. And that requires a few additional steps that we're going to go through in this section. And one more thing you should know about your task ENI is that in addition to your application's network traffic, there are a few other activities that happen over your task ENI. And those are the pulling of the image from either ECR or the public registry that you've stored your images in. And also, we have a feature where we can push logs from your application into CloudWatch. And that communication also happens over your task ENI. So when you configure the network around your task, make sure that these endpoints are accessible from your task. And in most cases, I mean, ECR and CloudWatch are public endpoints on the internet, and in most cases, public repositories are also public endpoints on the internet. So in most cases, you probably will need outbound internet access from your task over the ENI. So there are two common modes of setup that we think most applications will sort of fit into. The first one is where your task is private in that it does not allow any inbound internet access, but it still allows outbound internet access, either for the application's use case or for the image pull or logs pushing. And the second setup is a public task where it allows both inbound and outbound internet access over the ENI. So let's go through how you would go about setting up each of these scenarios. So private task setup. So this is the setup that we've previously introduced. You have a VPC, you have a subnet, you have a task that has an ENI with the private IP address from your VPC. You now want this task to not be able to take any inbound internet traffic, but still be able to send outbound internet traffic. So the first thing you will do for any traffic that needs to leave your VPC and go out to the internet, the first thing you need is an internet gateway. So you'll have to attach an internet gateway to your VPC. And now we're going to create a second subnet in our VPC, and we're going to call it the public subnet, because we're going to put all the entities that interface with the internet in this subnet, so it can be segregated from other private entities that don't interface with the internet. Now we need a way for things in your public subnet to then send traffic to the internet gateway that will send it out to the internet. For that, you need a route. So we associate a route table with this public subnet with the following rules there. And what the rules there are saying is that any network packet that's destined for 172.31.0.0, which is the private IP address space of the VPC, stays within the VPC. But any other address, any other destination address, will be routed to the internet gateway. So now we have a route for things in your public subnet to send traffic out to the internet. We need to put something in there that actually forwards the traffic out to the internet gateway. And what we're going to add in here now is a NAT gateway. So this is a VPC construct that allows exactly what we need. It allows private entities in your private subnets to forward traffic out to the internet using network address translation. So in this case, we have a NAT gateway. NAT gateway itself has a public IP, and it now has a route to send traffic out through the internet gateway into the internet. The other piece that's needed here is to now allow private entities in your private VPC to forward traffic out into to the NAT gateway, which is then wired to send traffic out into the internet. And we'll do that with another route table that's attached to your private subnet. And the rules in this route table look similar to the rules in the public subnet. The only difference is the local traffic still stays local within the VPC. The only difference is that for all other addresses that are non-VPC addresses, we're now going to forward the traffic to the NAT gateway in the public subnet. So traffic goes from your task that has a private IP to the NAT gateway that's in your public subnet and out to the internet gateway and out to the internet. All right. And one other thing that you have to remember to do is the security groups that you pass in on the run task API, you have to remember to allow outbound traffic on your security group in order to allow your task to talk out to the internet. All right, so what does the public task setup look like? And public task, remember, is both inbound and outbound access for the task with the internet. So you still need the internet gateway that we talked about. You still need a public subnet with the route that routes to the internet gateway. But this time, instead of launching the Fargate task into the private subnet, we're going to go ahead and launch it directly into our public subnet, because it needs to be addressable from the internet. And now you also need to give your task a public IP address if it needs to be addressed from the internet. So we have another field in the network configuration parameter of run task to assign a public IP to your task. Now this is a new feature that we launched for AWS Fargate, so please take note of that. And what this does is your ENI that we create will get an IPv4 public IP address that your task can then use to interface with the internet outside. And the security groups, again, remember, security groups that you pass in this scenario will have to allow outbound traffic to the internet as before, but also it will need to allow the requisite inbound traffic that you expect your task to take in from the internet. And once you actually run the task, make the API call, get a response, in order to discover the public IP address that was assigned to your task, you will describe the ENI that's been attached to your task, and that's how you'll know the public IP address that got allocated to your task. All right, before we wrap up the networking section, I think another very common use case is to keep your tasks private in your private subnet, but allow things on the internet to interact with your task through a load balancer that's public. So we're going to go through that setup very quickly. And as Dan mentioned on a previous slide, ELB integration is automatically and natively supported with ECS services. That's still true with Fargate. We do support ALB and NLB. And just a few pointers before we move on into the networking setup. Before you actually create the service with ECS, you will have to go into the ELB console and create your load balancer and set that up. And just a few pointers, when you're doing that, ALB requires you to pick at least 2 subnets in 2 different availability zones. That's a requirement of ALB, again, so that you can build redundancy into your load balancer. And ensure that the two AZs that you pick for your load balancer line up with the AZs of the subnet that you're going to launch your tasks into. That's what makes the routing work between the load balancer and the tasks. And also, the target group type that you will use with ALB will be an IP-based target, not the instance-based target, because in this case, we're going to be registering your task IP into the load balancer. All right, so how does the task definition change to tell us that you want to use a load balancer? You have to tell us about your port mappings. So in this case, our front-end container is listening on container port 8080, and our backend, or our API container, is listening on port 5000. And you need to put that into your task definition so we know exactly what port to register into your load balancer. And now this is the create service API call, which is similar to the run task API call that we've been seeing. It takes a task definition, takes the same network configuration parameter, and it also takes a load balancers parameter, where you give us an ARN to the target group that you've created with ELB, and you tell us which container amongst all the containers in your task definition do you want us to register into the load balancer, and what port is it listening on. So in this case, we're going to register our front-end container in our task definition into our ALB. All right, so back to our network picture here. The setup is very similar to the private task setup that we saw with the NAT gateway. You want to keep your task in the private subnet. It has a private IP address. It doesn't have a public IP address in this case. And in your public subnet, instead of a NAT gateway, you put a load balancer. You put your ALB in there, right? And your ALB, if you are using an internet-facing ALB, it gets a public IP address. And notice the ports in this case. Our Fargate task has a container that's listening on 8080 to accept incoming traffic from the load balancer. And the load balancer itself has a listener that's listening on port 80 to accept incoming traffic from the internet. Again, remember the availability zones on these two subnets need to match up. And then security group-wise, your load balancer is associated with the security group, and the load balancer has an inbound rule. The load balancer security group has an inbound rule that allows HTTP traffic into port 80. And your task itself has another security group associated with it. We don't want to associate it with the same security group because we don't want to allow inbound traffic from the internet on the task itself. So we associate it with another security group, and this security group has an inbound rule that accepts traffic from the ALB security group. So that's what allows traffic between the load balancer and your task that's running in the private subnet. All right. So that concludes networking, and we now know how we can launch a task into our VPC, configure the network, and really secure the network around your Fargate task using all the rich features that VPC makes available. And continuing along the lines of security, I now want to talk about identity and access management. And how you can use identity and access management is AWS's authentication and authorization service, and talk about the integration points that Fargate has with this service to how you can really secure the applications running inside of your Fargate task. And we have a number of tiers of integration with IAM, and we'll go through each of them. At the very top layer, we have cluster permissions, and what this lets you do is control exactly who can launch, stop, describe tasks within your cluster. And you can define policies on a cluster-by-cluster basis, as Dan mentioned previously, using IAM. And then you have your application itself that's running inside your task. And the application may need to access other AWS resources. So, for example, in our SCOREKEEP application, as Dan mentioned, we're accessing a DynamoDB table, or we're accessing SNS notifications. And each of these interactions need AWS credentials. And that also can be set up, as we will see in future slides, using IAM very easily on Fargate. And finally, there are a lot of activities that we perform on your behalf, just so you don't have to be bothered doing it, like the ECR image pull to actually get your containers running, pushing of logs to CloudWatch so you can actually see what your application is logging, the ENI creation and management for networking, the registration, deregistration of targets into your load balancer. These are all activities that we do on your behalf, and we require permissions from you in order to perform these activities. And that's also done via IAM, as we're going to see in the next few slides. So now I'm just going to step through each of these sort of in a little more detail so you get a more concrete idea of how this works. So cluster permissions, allowing specific actors to do specific actions within a cluster. And here is an example policy. So this is an IAM policy format that is essentially saying only allow run task API action against that specific cluster and that specific task definition family. Or here is another IAM policy that you may author, and this is a read-only policy that says only allow list tasks and describe tasks against that specific cluster. And these aren't the only policies you can author. There are many, many other examples, but I just wanted to give you a feel for the fine-grained policies, cluster-level policies that you can author and assign to various IAM roles or users that you've created to really ensure that you're giving the minimum set of permissions to various actors in your organization to do their job on Fargate. All right, application level permissions. And again, this is your application is accessing AWS resources. It needs AWS credentials. How do these credentials get passed down to your task? We certainly don't want you to hard code any AWS credentials into your container images. We also don't want you to be burdened with building orchestration software that sort of injects credentials into your containers at runtime. And so we solved that for you using an IAM task role. And how you would use this is you go into the IAM console, create an IAM role, attach the requisite permissions that your application needs. So in our case, we would attach DynamoDB and SNS permissions into the role. And you establish a trust relationship with ECS. And what this trust relationship does is that it allows us to assume that role on your behalf and do the credential management for you and wire your credentials down into the task in a secure manner. And then in your task definition, there's another new parameter there where you pass us the role ARN that you've created. And then that's all you need to do. Any AWS SDK CLI calls that you make from your application will then automatically use credentials from your task IAM role. And also these credentials, it's a feature of IAM, they're temporary credentials, they're automatically rotated periodically for you. All right, housekeeping permissions. Housekeeping permissions, as I mentioned before, allows us to perform management activities during the life cycle of your task. And there are two ways in which you give us these permissions to do our job to keep your task running. The first one is an execution role. And the execution role gives us permissions to pull your image and push your CloudWatch logs. So if you are using an ECR image, or if you are configuring logging to push to CloudWatch, you need to follow the steps in the execution role section that we're going to go through next. The other role in play here is an ECS service-linked role, and we'll go through the details of that, but the service-linked role gives us the ability to manage your ENI and your ELB. So looking at the execution role first. This, again, execution role used for ECR image pull, CloudWatch logs pushing. Similar to the task role experience, you'll go into the IAM console, create an IAM role, add the necessary permissions to read from ECR if you're using an ECR image, or to push to CloudWatch if you're using CloudWatch logging configuration. And again, you need to establish that trust relationship with ECS so we can assume the role and perform those activities on your behalf. And In your task definition, there's a second role parameter called execution role ARN that you will have to set with this role that you created. Service-linked role. A service-linked role, some of you may be familiar, it's a new-ish IAM construct. It's essentially a managed IAM role that's directly linked to a service, and in this case, it's ECS. It's very hands-off. It has a predefined policy. You don't have to actually go into the IAM console and create it yourself. You don't have to do any of these steps. I'm just going through it so you're aware. It has a predefined policy. Policy is immutable. It already has a trust relationship with ECS, so we can assume the role. And it's automatically created in your account when you create a cluster. So if you don't already have one of these, it will get automatically created when you create a cluster. So really, you don't explicitly interact with this role. The only thing is you may see it in the IAM console, and if you do stumble upon it, you know what it's used for. All right, logging and debugging. So with Fargate, your application is running on infrastructure that's hosted by AWS. So how do you actually see the logs or debug application problems? With AWS Fargate, we have native integration with CloudWatch logs. And as we've talked about before, you can configure your task definition to send any standard out messages that your application is emitting to CloudWatch logs, so you can then go into CloudWatch and view the logs or pull it down from CloudWatch as you please. So how do you go about configuring this in your task definition? You have to use we have an AWS logs driver that's already available with ECS today, and that continues to work with AWS Fargate. The setup steps that you will have to perform is you will have to create a log group in CloudWatch for your application, and then in your task definition, there's a log configuration section where log driver has to be specified as AWS logs. And in the options section, you tell us the log group name that you just created, the region, and a simple prefix, just so you can easily identify in the CloudWatch console what logs are coming from which application that you may be running on Fargate. And this is a screenshot of what it looks like in the ECS console. If you drill down into the tasks detail page in the AWS Management Console, we have a logs tab. And in that logs tab, you can essentially pick the container that's running within the task and view all the logs for that task within the ECS console itself. You obviously can also go into the CloudWatch console and view the logs in CloudWatch as well. Metrics. We also have CloudWatch metrics integration for ECS services. And this is also viewable in the console, in the ECS console, on the metrics tab of the services page. And the metrics that we emit are CPU and memory utilization for your service. What this means is we're basically telling you for the entire amount of CPU and memory resources that you've configured at the task definition level for all the tasks in your service, how much of it is your application actually using. So you get a good sense by looking at these metrics of have you over-provisioned or under-provisioned the resources in your task definition for the kind of application that you're running in it. It's also an important sort of visibility tool. Debugging tips. All right, so the logging, viewing of your application logs helps to debug things if your application has already come up and is running and is actually emitting logs. But if you're having problems even getting your application running, what kind of tools do you have to debug startup problems with your application? And just a few pointers here. This is a console snapshot for an application that I made it fail just so I can show you how it looks like in the console. First thing is you will see that your task never went into the running state. It will go, or it may have gone into the running, it will go directly into the stopped state from the pending and provisioning states. And there's status messages in the console for each container as to why the container exited. And in this case, you can see it's telling me that my task couldn't start up because it couldn't pull the image. And that's because if you see the image section right next to it, I've misconfigured the name of the ECR repository with like XXX and something like that. So the inspecting the container stopped reason will give you your first clue into why your application is not starting up on Fargate. Another scenario that may occur is that your services may not be scaling as expected, and how do you go about debugging that? So in the service page on the console, there is an events tab, and this is kind of like an activity log. If some of you have used autoscaling, they have an activity log that tells you exactly what autoscaling is doing to scale your instances up and down. We have a similar concept. We have an events tab in the service detail page that tells us exactly what activity we're taking. And if you inspect the messages here, you see that there's a few messages there. It tells you exactly what tasks were started at what time. You can even drill down into the task detail page. It's soft linked, so you can look at each task's details as they are started by the service. And then the very top one, for instance, gives you some details about why it was unable to start a task. All right. Finally, I just wanted to touch upon storage. With AWS Fargate, we do give you ephemeral storage for your task. It's backed by EBS volumes that we own. You do get 10 gigabytes per task of layer storage for your containers. And then we also make available volume storage. You get 4 gigabytes of volume storage per task. And I don't want to go into the details here to leave Dan some time for the demo, but the task definition has volume-specific fields in there as well, where you can specify mount points, and you can also share this volume across the multiple containers in your task definition. All right, now we're finally into the demo part, and you guys ready to see some action here? Yeah? All right. So this is what our final SCOREKEEP task definition looks like. It's basically, you should be able to recognize all the fields in here. It's split up into 3 pages, one for the task level configuration, and then each of your containers. We've gone through each of these settings, so you should now recognize all of these. The only additions here is the compatibilities field in blue on the first page. And that's essentially, as Dan mentioned earlier, we have retained all the same constructs between the EC2 mode and Fargate mode within ECS. So the task definition is also very similar between the two, but there are some fine rules there that not all fields in the task definition are supported on Fargate. For example, privileged mode, et cetera, is not supported on Fargate. So this field tells us if you're intending to run this task definition exclusively on Fargate, you can specify a compatibilities check that we will perform at the time of registering your task definition to tell you if it's compatible with Fargate or not. And if it's not, you'll know at task definition time rather than finding out at task runtime. You can also specify EC2 if you want to check compatibility with EC2. If you want the task definition to run on both Fargate and EC2, you can specify both of them. And if either of them fail, we'll let you know. And I think at this point, I'm going to hand it back to Dan to go over the demo.
So we have gone over quite a bit today, and the one thing I do want to point out is we've gone over a lot to really give you background about everything that's going on around your Fargate task, your cluster, your VPC, and so you can understand exactly what you need to set up. However, after setting it up, it is very easy to then go from having a CloudFormation stack that just sets everything up for you to then spawning new tasks, new services, modifying your task definition, and making changes. So I'm going to switch this over really quick. And hopefully you can see. So I have here a console view. This is the SCOREKEEP repository. And so I wanted to start there just to introduce you to the project if you plan on checking it out later. In the project, there is a configuration file called AWS env. This references a region Fargate is available currently in US East 1, and so that is set in the repository, as well as an account ID. And so this is the account ID that I'm using for the demonstration, and I can verify that by doing AWS IAM get user. And I can see that that account ID there matches. And so the scripts in the repository take advantage of this configuration file for pushing images to ECR and creating your CloudFormation stack. And so what I've done before the demo is I have a CloudFormation stack in the CloudFormation folder. There's a make file to make it easy to just create this CloudFormation stack, so I can say make stack. It's going to fail here saying the stack already exists because I've already created it in my account. I can then go back up. This root directory is going to be our API containers build process. It uses Gradle. It uses a Docker image to do the build. It then packages it up in a Docker image with Java and pushes it to ECR. And we can do this really quick with make publish. I've already built it, the Java file, and I've already published it to ECR, so this should be fairly quick to complete. And then next I have the SCOREKEEP front end. And the SCOREKEEP front end has, again, that Nginx configuration file as well as all the public files. That's the JavaScript and HTML for the application. And here as well I can do a make publish, and I can push that container out to ECR, and so it's all there. And next, I'm going to go into the task definition folder. And the task definition folder is going to be the task definition we created. Under the task definition folder, I have a template here. So I have a parameterized account ID and region. And so that from any AWS account, you can run generate task definition, and we'll substitute in those parameters that we configured in that aws.m file there. And so now I have this task definition created. I can go ahead and register it. So I can AWS ECS, register task definition. And I'm going to do the CLI input JSON mode. And so I've configured all my parameters in this task definition JSON file. And so I'm just going to pass it straight to the input like that. I will go ahead and copy and paste. And that registers my task definition with Fargate and with ECS. You'll see at the bottom here, this is revision 5. I have ran this a few times before, and so I do have 4 previous revisions in my account. Like I said, this is the family here is the SCOREKEEP application, and so this is going to be the 5th revision of it. With that, let's go ahead and jump back over to the AWS console, and I'll refresh it all. I have a default cluster created here. And that CloudFormation stack created the VPC, the log group, in the configuration that Archana mentioned. So I'm using a NAT gateway, and I have an ALB set up. I'm going to go here. I'm going to say create service. I'm going to select my SCOREKEEP 5, that task definition that we just pushed. I'm going to say that my launch type is Fargate. And then you'll see the reference to the platform version. I just want the latest platform version. The cluster, we're launching it into the default cluster that we just clicked into. I'm going to name the service SCOREKEEP demo. And I'm going to put 4 tasks. And so these 4 tasks are going to be balanced between 2 different availability zones because I'm using ALB, like Archana said. You want ALBs to be spread across 2 different availability zones. And so I'm going to say next, and that's where it's going to prompt me to select the VPC that I want to launch it into, as well as the subnets. Here is the SCOREKEEP VPC that my CloudFormation created, and it tagged it with the name SCOREKEEP, so it appears nicely on the side in this drop-down menu. And then I get prompted for the subnets within that VPC. I want to put this in the private subnets, and I've tagged the names as part of the CloudFormation template to SCOREKEEP private and public to make it easy to see and understand. And so here's one private subnet that I have, and here's the second private subnet that I have. I'm going to select security groups. I know I've already created a security group, and so I have here the default security group for my VPC, which is the one I'm going to select. And it is allowing ingress traffic to port 8080 from the ALB. So I can select that and press save. Because I'm in the private subnet and I'm using an ALB, I don't need to assign a public IP, so I'm going to go ahead and disable that. But I am going to select I want to use an application load balancer. For the load balancer, I have the SCOREKEEP LB. It's the only load balancer that I have created, and so it is set up there. And I have my 2 containers here, and I want to balance the one that's on 8080, that Nginx container. I'm just going to say add the load balancer. I don't have any listeners configured on my load balancer, and so I can create a new one straight here from the ECS console. The listener port I'm going to put on port 80, and so this is telling that when I hit port 80 on the load balancer, it's going to forward all the traffic to port 8080 in this target group. I'm just going to use HTTP. I don't have any certificates. The name that it generated is fine. I don't have a health check path. I don't have a /ping that's just an empty page. And so I'm just going to health check on the root page, which should return success. And so I'm going to say next step. I don't want auto scaling, so next step and create service. So this is going to go ahead and create the service and create the listener for the load balancer, and I can view it here in the console. So the tasks are going to start up now. The tasks take about an order of tens of seconds to start up. So it's going to be attaching the network interface, and then it's going to be downloading my Docker containers to the machine, and then the Java process is going to start up, and it will be accessible. So while it goes and does that, let's go ahead and just peek a little bit into some of the VPC configuration. So I'm going to go to the VPC console really quick and just show you a little bit more about what Archana talked about with the subnets and the route tables. And so in my VPC here, I have this private subnet. I can click on it. I can go to the route table. I can see that I'm using my NAC gateway. I can go to the public one, and I can see that the public one is using the route table that routes traffic to the internet through my IGW. Here you can also see on the NAC gateway tab, the subnet for the NAC gateway is in the public, and it has an elastic IP address assigned to it so that it can access inbound traffic from the internet. And now my tasks are most likely started up. Before going back to the ECS console, I would like to go to the EC2 console really quick and show you on the network interfaces tab. Remember, the Fargate task is creating network interfaces into your VPC. And so here on this particular screen, you'll see all the network interfaces that are currently in my VPC. And so I have the EOB network interface, as well as I have these other network interfaces. And you see the description here is AWS, ECS, US East 1. And so this is the ARN of the attachment ID for a network interface for our tasks. And so we see we have these 4 tasks using the default security group with the ARN, and that they are in use and they are available, and so they are started up. If you were using public IP addresses, you could see the public IP address that was given to the network interface here. Since we're just using private IP addresses, it was only allocated a private IP address. So we can pop back to the ECS console really quick, go back to our service, and all our tasks are all running. And so let's go ahead and see if we can hit these. And so I'm going to go to my load balancer. Instead of clicking that link, I have it open here. So I can just grab that DNS name and put it in the browser, and I have my SCOREKEEP app. And so I can type my name in. I can create a new game session. And then I can give a name to my game. I'll just name it Foo. I want to play tic-tac-toe. And go ahead and create it, and I can play that tic-tac-toe game. And this game is multiplayer, so you can use multiple browser sessions to interact and have multiple users join. I am just going to play against myself really quick and win. Can't lose playing against yourself. And so we see now that X wins. But let's go ahead and take a look back at our ECS tasks. And so we have this logs, and so I can pull up the logs here. I can click on the front-end container. And if I go through here, you'll see all the log statements. And so all those actions I just done on the web page, you can see the Nginx logs doing the API requests for making the moves that I did, for creating the game, as well as you see some health check logs from ELB hitting to make sure that my task is healthy. On the back end, I can switch it over to my API server, and I can see my API server logs, and I can see the tic-tac-toe statement moves. I can see my Java application booting up and all the information about it. If I go over to the metrics tab, they're not quite available yet, but you can use the metrics here to see your CPU utilization, your memory utilization of all your tasks. And you can use this to help guide and make sure that your task is actually sized correctly. And so if you are really low on memory utilization, updating it to a smaller Fargate task size is as simple as going to your task definition, reducing the size, and then calling update service with a new copy of the task definition. You'll then see that reflected in your memory utilization, and you'll be able to then save money by using smaller task sizes. And that's all I had for the demo today. We have a few minutes before we get kicked out to take any questions, but we'll be taking them on the side of the stage up here afterwards. We'll also be waiting out in the back if you guys want to stick around and have any questions to ask. We thank you guys all for coming today. Really enjoyed sharing Fargate with you.